Okay, so hello everybody. Welcome back to the Intercontinental Seminar Series on Gravity and Cosmology. So this week we are very happy to have Professor James Nestor to give a talk for us in this ISGC seminar. So Professor Nestor, he got his PhD in 1977 from University of Maryland. And then since 1985, he joined National Central University in Taiwan, and he's one of the experts, pioneering experts in the gravitational theory, in particular the duality between gravitational theory and gauge theory perspective. So today he's going to talk about gravitational energy and some insights from a Hamiltonian gauge theory perspective. So the stage is yours, James.
Thank you. Thank you. It's so nice to see you all here. Uh, Please excuse me, my voice isn't great today. I want to talk about work I've been doing over many years with my former students, Chen Changmei, Tung Shan, Gang Sun, and Liu Zhenliang. So let me quickly go over the abstract, because if I don't get to cover all the things I want to talk about, at least you'll have some idea of what there is in here. First of all, there's no consensus regarding gravitational energy. We are taking a Hamiltonian approach. From this perspective, energy is quasi-local. It's associated with a region's boundary, a closed two-surface. The choice of Hamiltonian boundary term needs a reference choice, and that reference choice reflects the chosen boundary condition. For GR, this framework includes all the famous proposed pseudotensors via their superpotential. We discovered recently that with a constant curvature Minkowski or ADS reference isometrically matched on the boundary, many distinct expressions that are formally distinct, including most of the pseudotensors, actually yield the same common quasi-local value. The application of our first-order Hamiltonian formalism, we've applied it to a large class of local spacetime symmetry gauge theories, including Poincaré and teleparallel, and I will briefly describe what those formulas look like for energy. Here are some references. I won't go through them. You can easily check this up on the archive or whatever. And there is a paper we're preparing, which should be done this spring, available. So where are we headed? The type of description we consider is quasi-local. That means it's determined by an integral of a two-form over a closed two-surface. You can usually think of this as the boundary of a spatial region at an instant of time. The boundary terms include both space-time energy momentum flux and spin flux density terms in general. These are associated with the space-time vector field and its first derivative. So there's a flux density associated algebraically with a vector field, and associated with the derivative of this vector field, a spin flux density. And these flux terms depend on a metric and its reference, a connection and its reference in general. And so we need a non-dynamical reference. I indicate that with a bar. That refers to the chosen geometric reference value. Now, let me say something about what does this mean to have a reference? Well, think about energy. When you basically learned about energy, what is physically meaningful is a change of energy, not the energy value itself, but the change in energy. So fundamentally, energy values fundamentally always need a reference. The way we set things up here, when the dynamical geometry values equal the reference values on the boundary, that's a special case, then the value of the boundary term will vanish. And so that will say the total energy momentum inside that region is zero. It's the vacuum, empty space, the ground state. That's what the reference means. The reference is a definition of what you're calling the vacuum or ground state. For a Minkowski reference, you can make that in terms of the metric, in terms of some local Minkowski coordinates. If you take a infinitesimal Poincaré transformation, so that has a constant term and a term linear in the coordinate, that's a local boost rotation. Then the value of the integral, if you substitute that into the integral I mentioned above, this integral will turn out to have a value that will be proportional to those constant parameters of translation and boost rotation. The coefficient of that determines the quasi-local energy momentum associated with that surface and the angular momentum associated with that closed surface. Now, the angular momentum includes in general both orbital and spin contributions. So although I often say energy, actually I mean energy momentum, and I mean energy momentum and angular momentum. Now, if you look at this angular momentum that includes orbital and spin, if you make a translation of the reference space origin, that's going to change the orbital angular momentum in a certain well-defined way. So the spin angular momentum is the part of the total angular momentum that's independent of such origin shift. It's described by the Pauli-Lubansky spin vector. So the magnitude of that spin vector determines the spin, and the magnitude of the energy momentum determines the mass. These are the two reference frame Poincaré transformation invariants. In other words, if you think of some region surrounded by some boundary S, you step far away, it kind of looks like a mass point with a certain amount of spin. A moving mass point with some spin. Now, we can generalize these instead of using Minkowski reference to have constant curvature reference ADS, then there's analogs of the spin and the angular momentum in that case. Let me go through some early history of this issue of gravitational energy momentum. In 1915, when Einstein proposed his field equations, he already had his energy momentum pseudotensor. It comes from the very beginning of the theory. Even before he had his field equations, he had a formula for the pseudotensor. This pseudotensor depends on the coordinate. That's why they call it a pseudotensor. It has no coordinate reference frame independent meaning. Well, many people were unhappy with this. Many objected. In particular, Lorentz, Levi-Civita, Felix Klein, Schrödinger. In fact, Lorentz, just in another year or two later, found a different pseudotensor in addition to the one Einstein had. Hilbert soon proposed an energy vector. Well, that really much puzzled the others. Nobody could quite figure out what this energy vector was. Actually, Klein in 1918 kind of worked out what it is, but nobody's paid much attention to that work by Klein. Well, anyway, Einstein understood all their concerns, but nevertheless, he believed that his pseudotensor was the best description, and it had real physical meaning. Not the pseudotensor itself, but the values that it described for energy and momentum. Well, this was quite controversial in those early years. And so you've heard about Emmy Noether and her two famous theorems. These were found in a paper of hers of 1918. Those famous theorems concerning symmetry in dynamical systems, that paper was written to clarify issues regarding gravitational energy raised by Einstein, Hilbert, and Felix Klein. Noether was a mathematician, not a physicist. She was interested in this as a mathematical puzzle. What does this system tell us? And she was able to clarify it. And there's a nice book on this by Kosmin Schwarzbach. Noether's results actually applies not just to Einstein's general relativity, but in fact to all geometric, that is generally covariant theories of gravity. And this is the basic message. Really, why she wrote her paper was to get this sort of conclusion. There is no proper conserved energy momentum density. That's essentially connected with general covariance. And we can see this reflected in certain modern treatments. An influential textbook states, and this is the book of Gravitation by Mr. Thorne and Wheeler. Anyone who looks for a magic formula for local gravitational energy momentum is looking for the right answer to the wrong question. Unhappily, enormous time and effort were devoted in the past to trying to answer this question before investigators realized the futility of the enterprise. I was a student at Maryland at the time that book was being written, and I was very much infused with that kind of concept. So I didn't pay any attention to gravitational energy momentum when I was a student there. That was something I learned about later, basically. Well, it turns out in our view now, this statement needs some revision and refinement. Emmy and Nutter, as I mentioned, had shown there's no proper local energy momentum density. Now it's recognized that gravitational energy momentum isn't described by a local density. It's quasi-local. That is, it's associated with a closed two-surface. Furthermore, some investigators do not regard this enterprise as futile. I'm one of Misner's students, but I didn't follow my teacher's advice. Furthermore, the efforts of many, including several Nobel Prize recipients, found many different expressions for gravitational energy momentum. We will explain that from a Hamiltonian perspective, all those expressions are physically meaningful. With the suitable reference, many of the proposed expressions actually yield the same common value, which could be viewed as the right answer. Let me say a little bit more about pseudotensors and superpotentials. Now, I should give you a little more background. My approach was Hamiltonian. I didn't originally start thinking about pseudotensors until somebody brought it to my attention that pseudotensors could fit into the Hamiltonian perspective. So then I began learning about pseudotensors and came to appreciate them. In 1915, along with his field equations, Einstein had proposed the pseudotensor. Basically, it's the canonical gravitational energy momentum pseudotensor, energy momentum that comes from his gamma-gamma Lagrangian. It's such that the total energy momentum density has vanishing ordinary divergence. So here's the total energy momentum. It consists of the material energy momentum and the gravitational energy momentum pseudotensor, and the divergence of this animal vanishes. That means it's a kind of conserved quantity. You can integrate this over a region, and it looks like it gives you some value for energy momentum. Of course, this integral depends on the choice of coordinates. So that's the puzzle, you might say. Now, from the fact that you have this vanishing divergence for this expression, think about it. Whenever you have something with vanishing divergence, by what mathematicians would call the Poincaré lemma, but it's something we know for a long time. Whenever you have divergence of something vanish, that means you can write that as a curl of something. So we could write this total energy momentum as the kind of curl of something. That's what the formula looks like. It's a first derivative of a certain superpotential with a certain symmetry. Now, it really is surprising to me when I think about it that none of those early researchers thought to look for such a superpotential. Not Einstein or Lorentz or Hilbert or Klein. It took another 20 years before Freud, out of the blue, came up with such an object. And there's the formula for it. It's linear in the connection, certain symmetry. Eventually, other people proposed pseudotensors. I had already mentioned Lorentz. Later on, from different superpotentials, Landau-Lifshitz, Papapetrov. The same one was also rediscovered independently by Gupta and later by Jakiev. And Bergman Thompson had a different one. Muller has another one. Weinberg, which was also independently found in the textbook of Mr. Thornwheeler. And they all follow from some kind of superpotential. Different choice of superpotential gives different choice of pseudotensor. All of these, though, would define some energy momentum values, which are, first of all, quasi-local. They depend on the closed-to surface, the value in a closed-to surface, and they inherently depend on the reference coordinate frame. That's why they're called pseudotensors. So people didn't know really what to do with this, and many people didn't think this had any serious physical meaning. It came as a big surprise when it was discovered that many of these fundamentally different pseudotensors gave the same energy value for all Kerr-Schild metrics, which includes many of the important known solutions. That's in a paper from 1996. I don't know how to pronounce the author's name, so I won't try. It was actually this work that stimulated my curiosity and opened my eyes to the possibility that pseudotensors might after all, be meaningful. Well, our recent discovery is much more amazing than what that work found. With a suitable reference, a very much wider class of expressions all give a common value. Let me say more about quasi-local energy momentum. It's associated with a closed-to surface, not a point-wise local density. Now, pseudotensors always were quasi-local, but nobody recognized this until Freud. And actually, the research community didn't really appreciate this very much until the 50s, and in fact, they didn't have the name quasi-local until Penrose, 1982. So the understanding of the this essential property was not recognized for a long time. Then, following what Penrose worked there in 1982, many people became interested in trying to find some quasi-local energy or quasi-local momentum. There's a comprehensive review of this topic that says, we have no ultimate generally accepted expression for the energy momentum and especially for the angular momentum by Shabadov. Now, there are different criteria that people use for their favorite quasi-local expression. The main quasi-local criteria are it should vanish for Minkowski. It should give the standard values at infinity, like ADM, at spatial infinity, null infinity, Bondi. And it should have positive energy. That's the tough one. In chapter 20 in the book Gravitation, Mr. Thornwheeler, you can find the acceptable asymptotic form for the 2D surface flux integrals for the total energy momentum. I paid no attention to that when I was a student. I learned about that in the 90s and studied it carefully since then. We found that any expression that has this form asymptotically agrees with what that text says in that chapter. That will give a good energy momentum value quasi-locally if you choose a suitable reference. Let me say something about the Hamiltonian perspective. This really clarifies the issues and the ambiguities. The Hamiltonian that involves a region along a certain like a volume, you think of it as a three-dimensional volume, along a vector field, it has a certain form. It involves the integral of a certain density or three form over the volume plus an integral over the boundary of the region. The volume integrand actually determines the evolution. If you think of the Hamiltonian evolution equations, when you vary that Hamiltonian, you do some integration by parts, the boundary term doesn't affect the local equation, the dynamical equation. It turned out when you analyze this, and basically this refers to Nutter's symmetry theorem, her second symmetry theorem, local symmetry. That volume term on shell, when the field equations are satisfied, actually always has the numerical value 0. In other words, this is proportional to field equations, this expression. That means the value of this integral only depends on the boundary term. Now, the boundary term necessarily depends on some non-dynamic reference geometry field. It determines the value of the Hamiltonian, which gives you the energy momentum and angular momentum, but it also determines the boundary condition. And this is what makes it not so arbitrary. There's a direct connection between those two. How do the boundary term determine the boundary conditions? Well, the boundary term in the variation of the Hamiltonian shows what you should hold fixed. So if you vary this Hamiltonian, you'll get some boundary term that tells you what you're holding fixed. What you're holding fixed will be controlled by what's in this boundary term. And that's then how, when you're evolving the system, how you're letting things flux through the boundary. So the ambiguity in the quasi-local energy or the pseudotensor is a function of different, let me say it this way, different quasi-local expressions correspond to Hamiltonians that evolve according to different boundary conditions. Here, let me show you how the pseudotensors actually point towards this Hamiltonian. Even if you didn't know about Hamiltonians and you were a pseudotensor guy, you can see how this leads you to the idea of the Hamiltonian. If you look at the energy momentum of a region, which comes from integrating the total density with some constant coefficients here, you imagine this to be a constant vector field in the present day, in the whatever coordinate system you're using. Then this produces the energy momentum. Now, if you take the definition of the pseudotensor, and which was a few slides ago, and you reverse that, and you do an integration, that gives you, this pseudotensor gives you the Einstein tensor and a boundary term. The boundary term is directly controlled by the superpotential. Now, this Einstein tensor value piece here, when the field, as I mentioned, when the field equation is satisfied, this vanishes numerically. So this is the Hamiltonian for GR. This is the covariant formula for the GR Hamiltonian. And here's the boundary term for GR. So the superpotential determines the boundary term to surface integral. The value of the pseudotensor Hamiltonian is thus quasi-local. It's determined just by the boundary term, since by the initial value constraints, the spatial volume integral vanishes on shell. The Hamiltonian variation, as I mentioned, gives information that tames the boundary term ambiguity, namely the boundary condition. The various pseudotensor values are values of the Hamiltonian with the respective boundary condition. Thus, one of the ambiguities of the pseudotensor program, problem one, is under control. We have many different pseudotensors. Well, they come from many different superpotentials. So there's many different energies. Well, that's not surprising. We know this from thermodynamics. We have internal energy, enthalpy, Gibbs, Helmholtz, different energies, each associated with a distinct system interaction across its boundary. Now, formally, if you look at our papers, you'll find we like to use differential forms, and we like to use the first order formulation, Hamiltonian, Lagrangian formulation. I don't want to go through all that detail today. I just show you what the formulas look like. The Lagrangian in general, quite generally for a formed field, K, is the differential of some of the field, and it has its conjugate momentum, and then there's a kind of potential that depends algebraically on the field and its momentum. If you vary this, you can easily see that you get a total derivative term, you get a term proportional to the variation of the field, and a term proportional to the variation of the momentum. The term proportional to the variation of the field is a term that includes the first derivative of the momentum, and the term proportional to the variation of the momentum includes the first derivative of the field. These are a pair of first-order equations. They're the dynamical equations we have. If you take those equations apart, those are four-dimensional equations for their forms. They have time components and space components. The time components contain time derivatives. The space components contain only spatial derivatives. Those are initial value constraints. So you get evolution equations and initial value constraints. Basically, these same equations can be found directly from a Hamiltonian 3 form. And the variation of this Hamiltonian 3 form has a term proportional to the field, and that has the time derivative of momentum, and a term proportional to the variation of the momentum, which has the time derivative of the field. The Hamiltonian boundary term, let's take a look at that. The Hamiltonian naturally splits into a part that is algebraic in this vector field and a part that includes a differential. From local diffeomorphism and variance, the Hamiltonian 3 form is a Noether conserved current. So its differential is always proportional to field equations. And we also find that this is proportional to field equations. So on a spatial hypersurface, the integral vanishes on shell, the volume part. The value comes only from the boundary term and is thus quasi-local. As I mentioned many times, but I want to keep emphasizing this. So if you take nothing else away, take this away. The boundary term in the Hamiltonian controls the boundary term in the variation of the Hamiltonian, which determines the boundary conditions. Well, we found a set of formal boundary term and Hamiltonian boundary terms and that are useful. This is a covariant symplectic boundary term choice. So delta phi here is the difference between phi and its reference value, phi bar. Delta p is the difference between p and p bar. Those are the reference values. Then the boundary term consists of two pieces. It has you can think of Z as the time evolution vector field. So you have the time component of either phi or phi bar multiplied by delta p, and you have the time component of p or p bar multiplied by delta phi with certain signs. Now, actually, these brackets, you don't have to pick either the upper part or the lower part. Those are the two canonical choices. But you can think of each bracket here as a linear combination with a one parameter. So like A phi plus 1 minus A times phi bar. So if A is equal to 1, you're making the upper choice. If A is equal to 0, you're making the lower choice. And actually, you can be interpolating in between. So those sort of correspond to kind of like Dirichlet or Neumann. Now, if that's the boundary term in the Hamiltonian, the variation of the Hamiltonian inherits some boundary term from that. And if you study the one that's printed here, this has some very interesting symplectic structure and symmetries. So you can see that we have basically Dirichlet and Neumann for respectively for the space and time parts of the field. So these two terms could each have a constant parameter, and we could have a different boundary condition for this piece and a different boundary condition for this piece. Now, this variation of the Hamiltonian, you can use this to calculate the energy flux. We did that in one of our papers. Now, finally, let me look at space-time geometry in a little more detail and the associated first-order Lagrangian. Space-time geometry, here we're only going to consider 4 dimensions, although much of this can be extended to other choices if you like other dimensions. And so we have a 4-dimensional space-time with Lorentz signature metric and a connection. We use the potentials we like to use are the metric, the coframe 1 form, and the connection 1 form, basically inspired very much by Friedrich Hale. There are associated field strengths, the non-metricity 1 form, the torsion 2 form, the curvature 2 form. So we have a general metric affine gravity first order Lagrangian 4 form. It has a term that has the differential of the metric times its conjugate momentum pi, differential of the frame times its conjugate momentum p, the curvature, which is basically the differential of the connection, times its conjugate momentum. Here I call it rho. And then we have some potential that depends algebraically on those objects. So that's the general shape of the Lagrangian. Certain special cases are easily imposed by taking the potential to be independent of the conjugate momentum fields, which then act as Lagrange multipliers to dynamically enforce a constraint. So for example, if you choose this potential lambda to be independent of this pi, then when you vary with respect to pi, this whole Lagrangian, all you get is dg equals 0. That's metric compatible. If you had chosen this potential to be independent of p, if you varied with respect to p, all you would get is this term from d theta, which is the coframe, which is the torsion 2 form. So if that vanishes, you have a symmetric connection. If you choose it to be independent of this momentum rho, varying with respect to rho will give you that the curvature vanishes. That's teleparallel. And you can mix and match, make combinations of these. There are many more things you can do, but a whole class of different theories can be put into this kind of general package. And this is just a sort of first order reformulation of what Friedrich Hale did back in 94 or so, something like that, on metric affine gravity. But here I'm just interested in what the energy momentum expressions look like. And to make things simpler, I'm going to choose a particular gauge because then things look really neat and compact. See, what's a little bit different here, as you know, notice maybe, the potential for the coframe potential, which is a kind of translational vector potential for torsion, and the connection That's a one. These are one forms, but the metric is a zero form. So this non-metricity has a different type of form nature than these others. But you can pick your reference frame so that the metric coefficients are always constant. That just amounts to using an orthonormal frame. Then locally, the general linear symmetry is broken down to a local Poincaré symmetry. And that makes things a little neater. But the more general formulas are also of interest. Anyway, let me just say what the boundary terms end up looking like. You then have a term that has, in terms of the time component of the frame, evolution component of the frame, times its momentum, and evolution component of the momentum times the difference between the frame and its reference. You have a similar term for the connection, similar terms. Now, this term actually is not covariant. These are covariant type expressions, but this one is not covariant. But if you pick an important special case of this expression, the special case where this p bar vanishes, your reference momentum vanishes, then I can tell you what our preferred choice is of this set. Now, this is a 1, 2, 3, 4, actually a 4-parameter set of possible Hamiltonian boundary terms, therefore possible energy momentum quasi-local expression. But this is one special choice that is pretty neat. In that case, the one we like is with p bar vanishing. That reduces to this term, and we make the lower choice here. So we eliminate this term. And here we make the lower choice, and we have this one, we make the upper choice. And then we use a certain identity that removes, because this expression so far still contains the energy momentum that is related to just a time-dependent Lorentz transformation of the frame. There's some energy momentum, angular momentum associated with that gauge freedom. To remove that, you can use this identity to reduce the expression to this form. Now, so that formula can be used actually for metric affine gravity. Even though we have non-metric compatible connection, we can still use this formula. You can use it for Poincaré gauge theory. You can use it for teleparallel theory. But let's look for GR in particular. For GR, the Hamiltonian boundary term, with using this eta variable, which is the dual coframe, we just get the term in the connection and the term that is in the differential of the vector field. The particular case we like is this version. And that's the first one we found. Chen Changmei found that in 1994 in his master's thesis at NCU. And about the same time, this was found independently by Katz, Bichek, and Lindenbell in a different notation. And over the years, we've come to recognize that this is really the best basic description of energy momentum. Like many other choices at spatial infinity it gives, with standard fall-offs, the ADM, MTW, Reggie-Table, and Biomer, Shabados, energy momentum, angular center mass. It also has some special virtues. It's 4-dimensionally covariant. At null infinity, it gives the Bondi-Troutman energy and Bondi energy flux. What does it correspond to physically? What's the implicit boundary condition? Holding the metric fixed on the boundary. That's pretty basic and fundamental choice for GR. Thus, this is the most standard, basic, natural, fundamental choice for GR. Not the only choice, but a rational choice, a reasonable choice for most problems. People are also interested in teleparallel theory. So we could go back to our earlier expression and kill the curvature by choosing the potential to be independent of the curvature's conjugate momentum. But in fact, we can get teleparallel theory in a very simpler way. The most basic teleparallel theory I know is what we would call pure coframe theory. Forget about having a connection. Forget about curvature and torsion and non-metricity. All we have is an orthonormal frame and its conjugate momentum. Then we can play the same games with this Lagrangian. Another path is that will take you to a certain formulation for teleparallel theory. Another path that you can get there begins from the general relativity equation that the metric or the Einstein 3 form, which is the curvature times this coframe combination, is equal to the energy momentum 3 form, material energy momentum 3 form. Rearrange this expression by basically extracting from this curvature a term that's in the differential of the connection, and then doing some integration by parts and rearrangement. You can redefine an energy momentum pseudotensor in terms of the curvature 3 form and then the differential of a superpotential. The total energy momentum 3 form density is this P. Then it simply satisfies D of our 2 form P is equal to our 3 form P. How nice. And then if we integrate that, we get the energy momentum in a region. Look how neat that is. Very neat expression. But that means that this value is actually quasi-local, given in terms of this P. Now, in view of the fact that you can split this R into D gamma plus gamma gamma, an obvious choice for this is to take gamma times this 3 form eta, this 3 index 1 form eta. If you write it out in terms of indices, it has a certain expression, linear in gamma. In a coordinate frame, this turns out to be the Freud superpotential. Whereas in an orthonormal frame, so you can, we haven't specified the frame yet, so this could be in a coordinate frame. It's Freud. This is another derivation of Freud. In a coordinate frame, it's Freud, but how about if we use an orthonormal frame? Then this thing is called the teleparallel gauge current. That's the name it's been given in modern times. But it was actually first proposed by Duan in 1963 in Lanzhou. And basically in Chinese, and nobody paid attention to it yet at that time, or much since then. There are other pseudotensor superpotentials, as I mentioned. Duda Lorentz and Landau-Lifshitz, Papapetro, Bergman-Thompson, Weinberg. Now we can extend these superpotentials. Normally they're written with respect to the components in some coordinate system. I want to make this a little bit more geometric. So suppose we have a reference geometry, and we promote this to expressions in terms of this reference geometry. Then this is what those superpotentials look like. I won't try to walk you through those expressions, but you'll see if you stare at them, you'll find that there's a lot of relationships between them, but they're not identical. And in fact, I can easily tell you how to make an unlimited number of other superpotentials that, beginning with these, you can make small adjustments, like replacing a metric by its reference metric or vice versa. to make a new superpotential with a new, your own pseudotensor, invent your own pseudotensor. All such things will define quasi-local energy momentum values, which depend on some reference geometry. Essentially, it's a Minkowski geometry assumed here that, and so basically it's a Minkowski reference frame. If you look in detail here, I have a superpotential for Lorentz and one for molar, and you'll see that they're closely related, one 2 times the other. I'll say more about that in a bit. Here. This is the basic superpotential form, but we can extend this further. Remember, I told you about energy flux and spin flux. If we want to get angular momentum, we need to include in general the spin term, the derivative of the displacement vector field. And we need to have a vector field which isn't constant, but which can be a linear function of the coordinate. If we look in Mr. Thorne-Wheeler again, section 20.2, guided by their formulas, we can construct flux density extensions of these superpotentials. Some of them follow a certain pattern. The flux density for some of them have the form an algebraic term that depends on the derivative of a quantity h plus a term upside. I failed to type in here that I should have derivative of z. This term should be proportional to the derivative of z. Derivative of z times this coefficient, which depends on the derivative of h. And not the derivative. Oh, I see. I failed to type in the z. Right there where my cursor is, if you can see it, there should be a z. I'm surprised that's the only mistake I've noticed so far today. Well, anyway, this H has the symmetries of Riemann. Now, you can find the explicit form of these for Landau, Lifshitz, Papapetrou, Weinberg, Mr. Thorne-Wheeler by looking at these expressions in detail. I was going to type them up, but I never got around to it. What about for Bergman-Thompson? Bergman-Thompson, their choice was vanishing spin flux. I don't think that's a great idea, but that's what they chose. We also found that twice the Lorentz flux density form is equal to the Komar flux density form, which turns out to be the same as Hilbert. This part here, twice the Lorentz one. This is actually Hilbert's energy the energy flux for Hilbert's energy vector. The extension of Muller's is Komar's formula, which is basically the curl of Z. So I know I'm saying this too fast, but what this is saying is we discovered that Muller's superpotential is just 2 times that of Lorentz. Now, Lorentz had a pseudotensor, but that was long before people had superpotentials. If you work out what the superpotential is, it turns out it's 1/2 of what Muller had. And if you take their respective flux extensions, Lorentz extends to Hilbert's energy vector, and Muller's extends to Komar's. So Komar's famous expression is just twice that of what Hilbert. Now, I want to say more about the reference space. How do we get a reference? We need a reference, but I didn't tell you how to get a reference. Well, the reference determines the zero of energy, the ground state, the vacuum. If the metric and connection have the reference values on the boundary, then the region is empty. It doesn't contain any energy momentum. The reference can be any space-time geometry, usually symmetric, maximally symmetric, a space of constant curvature, typical choice, de Sitter, anti-de Sitter. Then you have 10 killing vectors, and they would define 10 quasi-local quantities. Let's consider a Minkowski reference. How can we make a Minkowski reference? In the neighborhood of the boundary 2 surface, choose any 4 smooth functions, independent. They define a Minkowski reference. Call one the t coordinate, one the x coordinate, one the y coordinate, one the z coordinate. I won't take you through the how that goes into our GR quasi-local expressions because we're running short on time. But you can reduce the expression to a certain value, and then you can ask, it still depends on the choice of these, how can we determine what the coordinates are? Which Minkowski reference? There are two criteria: 4-dimensionally isometric matching on the boundary and energy optimization. Isometric matching on the boundary. To understand the idea, just imagine making a map of the Earth's surface region, a region of the Earth's surface. Slice a 2-plane through the region. That gives a circular boundary. On that circular boundary, the metric of the map exactly matches the metric of the Earth. But on the curved parts, there's some distortion inside and outside that boundary. So we do similar idea. We can embed the isometric 2 surface can be embedded into Minkowski. Basically embed based on a classic closed 2 surface into R3 embedding theorem of Weil, we can infer that there's a unique embedding as long as a certain expression, a certain modified metric has is convex. So that matches the metric on the closed 2 surface with the 2-dimensional closed surface in a Minkowski space. Then we still have some freedom. You can think of that Minkowski space, think of it first as embedding the 2 surface in a constant t hyperplane, and then think of deforming that hyperplane. That's 1 degree of freedom. And then think of getting an orthonormal frame associated with your final system, and imagine making a radial boost. That's the other degree of freedom. So I won't go through it here, but it's listed if you want to look at the things later, how many equations you have, how many unknowns. It turns out that if you have isometric matching, you still have 2 degrees of freedom. In other words, a typical 2 surface can be embedded into 2 surface in curved Riemannian space can be embedded into a flat Minkowski space, so that right on that 2 surface, the entire Minkowski metric matches exactly the flat metric, and that can be done in more than one way. There's 2 degrees of freedom in doing it. It turns out that if we do this isometric matching, many of those expressions I showed you earlier collapse into the same common expression. Basically, they reduce to Freud. So we've checked this with a lot of expressions, and for any closed 2 surface in a dynamical Riemannian spacetime, with 4-dimensionally isometric matching of a Minkowski reference, there's a common quasi-local energy value given by the expression that linearly agree with Freud approaching the Minkowski limit. That basically means that having the standard values at spatial infinity. So basically, if it vanishes for Minkowski and it approaches the standard values that asymptotically, then all these expressions will have the same quasi-local value. Here's a whole list of expressions. I won't go through them all that give the same value. Many different pseudotensors, but others expressions like Bichak, Katz, Lindenbell, Petrov, Katz, those expressions, Wang Yao. There are expressions that give other values. Hilbert, Lorentz, some of Goldberg's, Muller's, some the Witten expression with a certain value, Brown and York, Kiofsky's free energy, Liu Yao, Epp. And there are many quasi-local proposals that don't even fit into this Hamiltonian formalism, like Penrose's twistor and Hawking's mass and Sean Hayward's expression. Though that's not to say those aren't useful or valuable, but they don't fit into this framework. They are not the value of a Hamiltonian. Now, there's still an optimal choice because we have 2 degrees of freedom. Basically, we can look at the critical points of the energy to fix those degrees of freedom. That leads to a unique solution. Now, it turns out that our formula with this type of approach turns out let me just read this slide. Wang Yao in 2009, this was an outstanding achievement. They used a standard ADM 3+1 Hamiltonian approach. They used quasi-local expressions that were developed in the Hamiltonian approach of Brown and York and Lau and Hawking and Horowitz. With isometric matching embedding into Minkowski, they found a way to do the extremization and show that their quasi-local mass energy is non-negative and it vanishes for Minkowski. It turns out that one of my students, Liu Jinliang, showed that our expression agrees with Wang Yao's in this limit. Now, Wang Yao also have an angular momentum, and I don't know if their angular momentum is the same as ours or not. But anyway, by way of Wang Yao and my students' work, for all the asymptotically good expressions, not just ours, but all the others I've listed, a non-negative quasi-local energy exists which vanishes if the dynamical spacetime is Minkowski. This quasi-local energy could have been found actually, didn't have to wait until these days. It could have been found any time since 1939. People spent a long time looking for the best energy expression, including me. We investigated the Hamiltonian boundary term and found our reference-dependent expression. Only after we found a good expression did we look for a good reference. But if we had just taken any asymptotically good expression and looked for the best reference, we would have found this desired energy. So here's the complaint. Gravitational energy is ill-defined. There's no unique quasi-local expression. Reference frame-dependent expressions with no unique reference frame. But we discovered with a 4-dimensionally isometric reference, most expressions give the same value. One can find an optimal reference choice, hence a well-defined energy momentum and angular momentum. Einstein with his pseudotensor was close, and so were many others. As Nutter in the textbook said, there is no proper energy momentum density. It's now understood that if not local, but quasi-local. And although there was much effort extended to finding the best expression, there still is no single accepted quasi-local expression. But we discovered that a consensus on the expression is not needed. Associated with any expression for a large class of reasonably proposed expressions which satisfy basic simple criteria, there's a well-defined energy value which does have the desired property. Here's some detail on a constant curvature reference. I won't go into this. Basically, this is Abbott and Desser, who wrote down the formula for the total energy momentum for a constant curvature asymptotic anti-de Sitter space. And basically, if you look at their formula, it's exactly this kind of energy flux expression I told you about. In fact, it's exactly what we get if we take the work in Mr. Thorne-Wheeler and extend it the way I described. In different notation where I had an H, they now have a K. Basically, that's it. In other words, but they're proposing it at infinity, basically, at infinity, but we can just use this quasi-locally. But then you have to choose the reference. I won't take you through the detail here. So let me just review again the whole picture. Gravitational energy was assumed to be ill-defined, no proper expression, many boundary conditions, many local expressions. Reference frame-dependent expressions with no unique reference frame. Using a Hamiltonian approach, we discovered there's a natural, uniquely distinguished quasi-local expression associated with fixed metric boundary conditions. If the boundary surface can be isometrically embedded into a region of constant curvature with a time-like killing field, then any expression equivalent to certain expressions that give well-behaved expressions will give the same quasi-local value. Basically, it's Freud and Abbott-Desser. If they agree with Freud and Abbott-Desser, you'll get the same quasi-local value. The critical points of this energy determine an optimal embedding and optimal quasi-local values for energy and spin. For a Minkowski reference, the quasi-local energy is the non-negative Wang-Yao mass for GR. An optimal isometric reference gives a unique quasi-local energy. Thank you for your attention and patience.
Thank you very much, Professor Nestor, for the nice talk. So, is there any questions from the audience?
Maybe I have a few.
Yeah, sure, please.
Hello, Jim.
Yes.
I like your talk very much. Very interesting. But I'm a little confused because I think I'm a more practical guy. When I think of energy, I think of it as something as observable. For example, I think about the binary pulsar system.
Yes.
And that's how we know that gravitational waves exist before we even detected it.
Yeah.
So am I understanding correctly that Einstein used his pseudotensor to go on to derive the quadruple formula? Is the same pseudotensor that you talked about that Einstein derived?
I think he derived the quadruple formula from this pseudotensor formulation. Yes, I think so. But yes.
So I'm wondering.
But maybe Wado knows better than I do about that.
Because I'm just wondering about what the observable consequences are in terms of, because you say there's no, even till today, there's no kind of consensus on what gravitational energy is.
Yes.
But so I wonder about the observable consequences of these different choices, so to speak.
Yes. I think you raise an interesting question, a very interesting question. There are many, many different ways to define energy and talk about energy, and many useful ways that are practical for some purpose. The things I'm talking about are actually, I never set out to find energy. I set out to find what's the correct way to choose the Hamiltonian boundary term. And I assumed that the value of the Hamiltonian What's the meaning of that? Well, it defines an energy, basically. That's the basic framework. Now, how can we actually measure this? In practice, it wouldn't be very easy to measure. Think of trying to find out how much energy momentum there is inside the room you're in right now. What you have to do is you have to measure the metric and the connection on all the walls and the ceiling and the floor at every point. And then plug it into a certain formula and do a certain integral. It's sort of like a Gauss flux integral.
But can it be converted into an
that doesn't correspond to something you would measure locally.
But what about experimentally? Like, can I devise at least a thought experiment to get at what you're calculating?
That's a good question, and I think somebody should pursue that.
Can I say something?
Yeah.
For gravitational waves, it's a little bit repeatable, and Isaacson in 1968.
Yes.
He did an average of that in a background. So that is what we do experiment in the solar system. So that has no doubt, and one can use stress energy tensor, the standard form for gravitational waves. So it's no problem.
I had the impression that Isaacson assumed some kind of vacuum background. Is that not right? Because he also used WKB, averaging, and WKB, and so on.
That's right. So that's what we do. We do average or integration in gravitational wave detection. So it's in a background metric of our solar system. And even in galaxy, our solar system ephemeris actually use a quasi-Minkowski metric. So it's not a problem for detection.
But for example, even in de Sitter background, over the past...
that's another matter.
10, 15 years, the quadruple formula has been extended to at least the de Sitter background.
So that's no problem with Isaacson's investigation. So his work is on a smooth background. So that means gravitational wave has a little bit higher frequency than the curvature scale. So it's not a problem.
But for example,
theoretically for practice.
I do understand what you mean. I think in the high frequency limit, what he does is probably the leading order answer, right? But what I'm wondering about is, for example, what Jim is doing presumably can recover the quadruple formula in, say, de Sitter. Would you say that, Jim?
That's a good question. I would imagine so.
It's correct. It's correct. I mean, since Isaacson work in 1968, his work is on a background, a smooth background. So if you say something into collapsing, or if you say something in binary coalescence, then you have to design a measurement there. Then we can discuss.
But I don't think he actually got a quadruple formula in a general background, isn't that right? My impression was that what he did was more of the propagation of the waves, and I need to review it a little bit. But but so I am wondering whether Jim's formalism can directly be used to get, for example, what this actually was first derived by Ashtakar's group. I think it's now probably 15 years ago now, but there is now a known quadruple formula in de Sitter spacetime, and so, for example, I would consider that observable in the sense that you can use it to predict if, let's say, you have a binary system not in Minkowski, but binary system in de Sitter instead, and then try to use that quadruple formula to predict the energy loss, then that is an observable, I would think. Right. And I think what Jim is doing here, I'm assuming can be translated into that. I'm wondering. It's more of a question.
Yes.
Okay. Yeah. Because I actually personally have been interested in generalizing it to more non-trivial cosmological backgrounds. And
Yes.
yeah, I know the corrections will be small, but theoretically speaking, it should still be non-trivial.
Mm-hmm.
Yeah.
Yes.
Yeah. Okay. Thank you. Thanks very much.
Yeah. These are interesting questions.
Yeah.
Any other questions or comments? So maybe I can also ask one, which so James, you mentioned there are a few quasi-local expressions which even do not fit into Hamiltonian approach.
Yes.
So then how do people even compare this those expressions, whether they can give a consistent or agreement with those with Hamiltonian
Well,
description?
it depends on what you want to do with your formula. Just like even thinking some physical thing like how can you compare the enthalpy with the Gibbs free energy?
Oh,
You know, that uh, they they are suitable for some different observation and application. They're a good tool for that purpose. But uh, for example, here's what some people often say. We can define an energy associated with a gravitational field as follows. Let's put a test particle in orbit around a mass. And we use Kepler's law basically to calculate the mass, and then we say E equal mc squared. And that's certainly a very physically meaningful, observable thing. In fact, more practical than my surface flux integral. Because to do a flux integral, you have to have a completely closed surface with information all the way over this closed surface. It's like a Gaussian flux integral to find the charge inside. Similarly, we're finding the energy or spin inside, but by doing an integral over a closed surface. So formally, this is a very meaningful thing to do, but how to connect this to a practical observation and useful application? Yeah.
I see.
But for example, we can do this with the because my closed two surface can be any closed two surface. You can take its limit to spatial infinity, but you can take its limit to future null infinity. And then you get a Bondi-like quantity.
I see. And can you even apply that surface to the case of like black hole event horizon, even like for dynamical evolution of black holes? And can we use this approach to really identify like the energy associated with the evolving black holes, or even during
That's
mergers?
how to do something practical with this, I don't know. Certainly, simple solutions like Schwarzschild you can calculate
Yeah,
very easily,
sure.
And you find that the quasi-local energy at infinity is the ADM mass,
Yeah,
and at the horizon it's twice the ADM mass, which is what Brown and York found first. They were the first guys to find it. And a similar property happens for ADS or Schwarzschild ADS. I don't remember the exact numbers, but yeah.
I see.
Yeah.
Thank you.
But how to do this for something that's actually very dynamical?
Yeah, that's
Well, in fact, if you imagine taking your surface and you imagine deforming it a little bit, you can push it in a time-like direction, so it makes a kind of cylinder then, and you can compare the values, and how you evolve the surface will depend on what number you get.
hmm
Yeah. Yeah. So formally, one can study these things, but not now. This I should make very clear. In our approach, the reference we defined there was an instantaneous reference. So, the reference, we have a closed-to surface. We associate a certain
Time
particular
size.
reference to a neighborhood of that closed-to surface. Basically, it's like patching the nearest Minkowski space to that neighborhood and comparing with that. But if you move the two surface a little bit, you change that reference a little bit. So the reference isn't constant. Well, actually, in the original basic formula, before you choose the reference, you can choose the reference to be anything you want. You can choose it to be a globally fixed solution, like maybe it's Minkowski or de Sitter or something. There's nothing to prevent you from doing that.
Yeah.
But the choice of isometric matching choice of reference, which makes the thing quasi-local. It defines a reference that you don't have to go off to infinity to find the reference. You don't have to go to infinity to know what zero energy means. You can define zero energy based on what would the Minkowski metric be that would have the same values on the boundary of the region I'm in
hmm
exactly on that boundary.
Sure.
But we empty Minkowski space inside.
Yeah, I
And you
see.
compare it with that.
I see. Thank you. Is there any other questions? If no, then maybe let's thank Professor Nestor again, and let me stop recording.